So we have the gravitational force, and usually, at least in high school, you say F is equal to gmm over r squared and so on, right? But what makes a lot more sense is to talk about the acceleration, because the acceleration of all particles is the same. So you could imagine an acceleration field outside of mass. Here's the Earth. Outside the Earth, at any point, we can compute what the acceleration would be of any object, whatever size, whatever shape and mass, etc., density. We know exactly what the acceleration would be. Acceleration would be such and such amount in that direction. Over here it would be the same amount, but in that direction. Over here it would be a little bit less, and so on and so forth. So instead of talking about a force, and then having to figure out how that force affects different particles, what we do is we talk about an acceleration, a field in space, and the acceleration that any particle will experience in that field.
Here's spherically symmetric mass, and we have outside here a force g and m over r squared. Now, of course, as a result of the equivalence principle, we can write acceleration divided by the mass, and we get gm over r squared, which means that at every point in space outside this mass, we have a radially directed acceleration with an amount equal to gm over r squared at every point. Now, this is very nice because what that means is that we have an acceleration field. And this is something that can only be done in gravity. If you're having, for example, an electric field or any other kind of field, then you have to use F, the force field, because the resulting acceleration of this force, let's say it's a QQ over r squared force, the resulting acceleration will be QQ over r squared divided by m, force over mass. So you're going to have to talk about a force field. If you're talking about gravity, you can uniquely define an acceleration field rather than a force field. So gravity produces an acceleration field. What that means is that at any point in space, at a given time, you have a bunch of particles. You have a particle moving with a velocity in this direction with a certain speed. Another one is moving like that. Another one is moving like that. Whatever. As they cross this point, if they're crossing here simultaneously, let's say, if it's a static field, it doesn't matter, then they all experience exactly the same acceleration, irrespective of their mass and irrespective of their initial conditions, their speed and direction. And that's why you can uniquely define at each point in space the acceleration field. And we don't really care, in terms of basic physics, about the initial speeds and directions of some particles. Those are like particular examples to solve later. The theory is built on the fact that you have a field in the space around this spherically symmetric object, and it's an acceleration field given by this.
Well, we know that gravity affects all masses in the same way. Right now, you're experiencing weight. Your weight pulling down, but actually what you feel is not your weight. What do you feel now? Do you feel your weight on you? What actual force do you feel?
The normal force.
The normal force, resisting the weight. There are non-gravitational forces at work in the floor and the chair, and they're helping you resist. The gravitational force is pulling you down, and the non-gravitational forces are pushing back up, so that the sum of the forces are zero. So what you're feeling actually is a force upwards. Now what's interesting, if we take everybody and every object here, we all have different masses. Maybe we have different densities, there's tables, there's chairs, people, and so on. But if you divide by each person's mass, so you take their weight divided by the mass, what remains? It's a quantity that we don't really have a name for usually, but what are the units?
Could you repeat that?
When I'm standing here, when you're standing or sitting and watching this, what are you actually feeling? We discussed this. You're feeling the normal force on you coming from the non-gravitational forces, the electromagnetic and basically at the end the quantum mechanical, etc. forces in all the materials, and that's pushing up on you, and that's what you feel. And if you take everybody and all the pieces of furniture and they have different masses, some of them large mass, some a small mass, and whether they're sitting or standing, they're going to be feeling different normal forces. The one with the large mass is going to feel a weight that is determined by its mass, and this one is going to feel a weight determined by its mass. And it's going to feel this normal force due to its weight. Now, if you divide by the mass, of course, you end up with G. So there is an equivalent accelerative push up that's exactly equal for all of them. Okay, so we all have weight. The weight is basically the gravitational force on us, right? Obviously, the weight of everybody here and every object in the room is different, but partly because of size, partly because of density, and so on. So everybody has a different weight. But if you divide everybody's weight by their mass, what will remain?
The acceleration, or gravitational acceleration.
It's not exactly gravitational acceleration, because gravitational acceleration is something that actually moves down. But what remains is basically exactly the same as the gravitational acceleration, something with units of acceleration and the amount of the gravitational acceleration, but it's some kind of a push acceleration upwards. Okay? And it's identical. Everybody's push acceleration that they're experiencing is exactly identical because it's mass independent. The weight is the gravitational gm over r square, m of the Earth, times your mass. Your acceleration is that divided by your mass. So it just leaves the gm over r square. So everybody, although they have different masses and densities and different weights, has the same amount of gravitational push acceleration, which is, again, it's coming from the non-gravitational forces of the floor and the chair. They're pushing back up. But what you're experiencing is an acceleration upwards. But what you're experiencing is an acceleration upwards. Now that acceleration is indistinguishable from what? What other physical situation would give rise to exactly this same phenomenon? A whole bunch of people in one place, and they're all experiencing exactly what we're experiencing now, in sense of the actual feel of it, and in the physical sense, the mathematical sense that we just described, that we all have acting on us an upwards accelerative push, so to speak.
Are you talking like centrifugal force or centrifugal?
Something, yes, something like that. But let's say what would give rise, you're right, but what would give rise to exactly this? We're all sitting in a room and we feel a force upward, centrifugal force be pulling you to the side and so on. Just to give an exact example, you imagine this building.
Like it goes accelerating.
Exactly. If this building was an empty, distant space, there's no gravity around anywhere, but the building was accelerating in this direction, we would feel exactly the same thing. And we would measure exactly the same thing. It doesn't matter what piece of furniture or what person or what mass or what density or what size, there's an accelerated push upwards. And as we mentioned, that is completely indistinguishable from some kind of an interplanetary building, rocket, which is all the way maybe in intergalactic space, totally empty of matter. There's no gravitational field that's measurable, and there's nothing even visible, maybe no galaxies visible anywhere nearby. And everybody in that building is feeling that acceleration. And since it's just an acceleration, then obviously it doesn't matter if you're on the third story or the second story, the first story, or what side of the building you're on, you all have exactly the same acceleration, and therefore you're going to feel exactly the same accelerative push, so to speak, on your feet, irrespective of your mass. Obviously it doesn't depend on your mass, it depends on the acceleration that this rocket ship building has. So there it's no surprise. What's surprising is that in gravity it happens that way, that everybody here feels the same accelerative push. And that's why we can model what's happening here in this building on the planet Earth with an intergalactic traveling spaceship building. And Any measurement that we make will be the same in both. They're indistinguishable. So a strong equivalence principle claims that any physics experiment that one would make in empty intergalactic space in this interplanetary rocket building would give exactly the identical results. An electromagnetism experiment, light experiment, anything will give exactly the same results as here on planet Earth. In other words, if you want to know how does gravity interact with some other force phenomenon, and you wanted to do an experiment here in the lab, and you were wondering how to do the equations, you could, if you want, just go into intergalactic space and do the experiment there in a rocket. Now, of course, you say, well, it's kind of difficult, I don't have the budget for that. So what do? So we can do just ignore gravity, pretend there's no gravity, and just write the equations for an accelerated platform or rocket or building, whatever it is, and put in your phenomenon there and just see how it would work in an accelerated frame.